Hello everybody, we are group 37 and our project name is UCF GO. Our group consists of 4 participants, me, Caio Loureiro, Chandler Earp, Jaron Wilson, and Marco Murati. The University of Central Florida is the largest university by enrollment in Florida, hosting classes for over 72,000 students. He has over 2,000 instructional staff and many other employees that utilize its parking services. Now the question is, how does UCF handle that many vehicles every single day? UCF has a total of 7 parking garages for students and employees, each holding from about 1,000 to 2,000 vehicles daily. Finding a parking spot during rush hour can be very complicated, but what's more complicated is remembering where you parked your vehicle after having to pack up your things and rush to class. The birth of our idea came from this problem. Our idea is derived from a shopping mall business model. We would like to save the user's vehicle's location and show it on a map after he or she has parked the car. Our mobile app would connect to each individual parking spot through a QR code, and once scanned by our hardware, it would transmit the data with the user's location. In other words, how does it work? So the user parks, the hardware sensor scans the QR code on the parking spot, and through Bluetooth, the sensor would transfer the data to the user's mobile phone, and the location would be displayed on the app. Our motivation came from wanting to make people's lives easier. We know how much stress students and even staff are under during their daily routine, and this is something that everybody could benefit from. We also loved the idea because of how big of a challenge it was to our group and to our personal development. Our main goal is to help the UCF community by developing an app that is fully functional with user-friendly accurate location and accessible to as many people as possible. We will also design a hardware device with a car detection feature and implement Bluetooth connectivity. In selecting parts, you must balance the trade-offs of different components between engineering and user requirements. Understanding these relationships within a project can help narrow down the design requirements and reach an end solution. Using a house of quality figure is a great way to represent the trade-off matrix between user and engineering requirements. And in this picture is the house of quality matrix for UCF GO. For our project design approach, a lot of things were put into consideration, such as budget, app compatibility, app usability, the sensor and the car size, and the weather.
This is the block diagram for our project design. As you can see, there are 2 main subsystems for our project, the parking location subsystem and the garage availability subsystem. Starting with the parking location subsystem, it is centered around a microcontroller that is mounted to the user's automobile. The microcontroller is outfitted with a camera that scans a QR code located at the parking spot, a Wi-Fi module that it uses to transmit the location information stored in the QR code to the database, as well as a power system to power the microcontroller. Next is the garage availability subsystem. The garage availability subsystem is centered around a custom PCB with a PIR sensor, a Wi-Fi module, and a power system. The PIR sensor detects motion when a vehicle is entering the parking spot and transmits that information through the Wi-Fi module to the database. The database then uploads this data to a web application which is reflected on the user's smartphone on an Android application. Each of the blocks is color-coded to designate which team member is primarily responsible for it. This slide shows the project design for the garage availability subsystem. As previously mentioned, the design is based around a custom printed circuit board. We prototyped this design on a breadboard using the Texas Instruments MSP430 Launchpad. The garage availability subsystem has two main components: the HCSR501 PIR sensor, shown below, and the ESP Room 32 microcontroller, shown in the bottom right. The PCB subsystem is mounted in a front-facing position on a given parking spot. The PIR sensor's function is to detect the motion of a parking car and update the database accordingly. A microcontroller is often used to control electronic devices in an embedded system. A microcontroller can either be a single chip or several components on a circuit board that act as a small computer. For our project, we need a microcontroller in order to take input from the sensor, analyze that data, and send it over to the transceiver. During the part selection phase of our project, we considered three different microcontrollers to base our design on. We considered the ESP32, the ESP8266, and the ATmega328. For our comparison, we used specifications such as the number of cores, the architecture, the CPU frequency, whether or not they had onboard Wi-Fi and onboard Bluetooth, the amount of RAM, the amount of flash, the number of general-purpose input-output pins, and finally the price. For our design, we chose to use the ESP32. While being the most expensive of the three microcontrollers, it offers the highest performance and the most versatility for our project. On the left, you can see an image depicting the internal schematic of the ESP Room 32 microcontroller. On the right, there is a variety of specifications that are useful to our project. Significantly, there is powerful onboard Wi-Fi and Bluetooth chips with useful features such as Bluetooth Low Energy, a variety of module interfaces, operating voltages and operating currents, fitting for a battery-operated device, as well as a small package size. A sensor detects or measures a physical property and responds to it. For our project, we need a sensor to be able to detect a car pulling into a parking spot. Several different types of sensors could work for this application. On the left, there is a flowchart depicting the basic functionality we need out of a sensor. We need the sensor to take a reading, compare the current reading to the previous, and if there is a significant change, update the occupancy state, and then transmit that occupancy state before sleeping for a designated time. If there is not a significant change, then the sensor can go straight to sleeping for a designated time. When selecting the sensor to use with our design, our team chose between three different sensors: the ultrasonic sensor HCSR04, the infrared sensor HCSR501, and the piezoelectric sensor. Any of these three would have been able to detect the motion of a car parking in a parking spot, but ultimately we decided to use the HCSR501 passive infrared sensor. What drew us to this choice was the modest price as well as the minimal current draw when in passive mode. This means longer battery life for our device. On the left, you can see an image depicting the internal schematic of the HCSR501 PIR sensor. On the right is a table of specifications of the sensor. The operating voltage from 4.5 volts to 20 volts. However, with a slight modification to one connection, we were able to make the sensor functional at 3.3 volts. The operating current, the static current, the high and low output values, the adjustable delay time by an onboard potentiometer, the maximum sensing range, also adjustable by an onboard potentiometer, the operating temperature, and the small dimensions of the sensor. With our two major components selected, we began to design the PCB. On this slide, you can see all of the schematics for the PCB design, including the power regulator, the output drivers, the GPIO headers, the output connectors, the indicator LEDs, as well as the main ESP32 module. On the left, you can see the actual PCB layout. On the right, you can see our bill of materials. The bill of materials consisted of a variety of LEDs, 2 pin header strips, a 3.3 volt voltage regulator, a variety of resistors and capacitors, 3 terminal blocks, the ESP32, and 3 MOSFET transistors. This slide shows a gallery of the final PCB implementation. We received the PCBs from the PCB house already with the surface mount components assembled. All that was left to do was to solder the ESP32, the 3 terminal blocks, and the pin headers. We then prototyped and tested the connections with the sensor before finally installing it in a custom 3D printed PCB enclosure and connecting it to a portable battery so that it was ready for deployment. This is an overview of the garage availability software. The ESP Room32 MCU was programmed with a serial to USB programmer. It was flashed with C code written in the Arduino IDE to take input from the sensor and connect to If This Then That, which is a service that programs responses to events. If This Then That then updated a Google Sheets spreadsheet with the occupancy state of a given parking spot. Google Apps script then connected the data in the Google Sheet to the database. The data in the database was finally presented to the user within the mobile app. Here is a basic flowchart of the connections that made the garage availability system possible. From the PIR sensor to the ESP32 to the service If This Then That to Google Sheets and finally to MongoDB. This is a summary of the testing for the garage availability subsystem. The first test was the time for the ESP32 to connect to the internet, expected to take 5 seconds, and the result was 3.35 seconds. The time for the MongoDB to update after the sensor has been triggered, expected to take 2 seconds, actually took 1.62 seconds. The minimum range of the HCSR501 PIR sensor was listed as 3 meters. In actuality, it worked out to be a little bit more at 3.7 meters. This did not end up to be a problem because the UCF parking spots are slightly deeper than a standard 3-meter parking spot. Then finally, the HCSR501 PIR false positivity rate, we decided an acceptable amount would be 10%, and in testing we found that it was only 4%.
Project design. User location subsystem. To store the location of the user, a Raspberry Pi 3B is used as a microcontroller for a camera to scan a custom QR code that contains data for each individual parking spot. The camera microcontroller consists of 4 components: a Raspberry Pi 3B, a step-down voltage regulator to micro USB, a 7-inch touch LCD screen, and an ArduCam Day-Night V1 camera. Raspberry Pi 3B microcontroller. The Raspberry Pi 3B was chosen as a microcontroller due to its affordable price, great adaptability to many projects, and the fact that one was already owned and we were able to start working on it instead of waiting for a new chip to arrive. While there is a newer version of the Pi, the Raspberry Pi 4, this was an upgrade we decided was not worth considering the specifications of the 3B were more than enough for our project. A step-down voltage regulator with micro USB. To power the microcontroller with a car battery, we use a waterproof step-down voltage regulator to micro USB, which safely powers the microcontroller as it converts the 12 volts output of the battery to a 5 volt with 3 amp current. A 7-inch touch LCD screen. For the user to access the microcontroller application, we use a 7-inch HDMI LCD touchscreen, which is powered by the camera microcontroller using a micro USB and an HDMI. This allows the user to use the GUI and watch in real time the camera in front of the vehicle. Camera comparisons. We compared multiple cameras to see which one was best used in our project. The idea behind using a camera to scan the QR code instead of a laser scanner was that it allows for troubleshooting. We felt that it would increase the comfort levels of the user if they were able to see the code being scanned instead of just parking and hoping the scanner was lined up. Out of all the cameras, we chose the ArduCam Day-Night V1 camera. Compared to the other V1 and V2 cameras, the ArduCam has superior specifications such as resolution, field of view, and a day-night sensor. Using the CSI port of the microcontroller and Python's CBAR library, This allows for the camera to run smoothly in real time. Camera microcontroller software. Python 3 was used to program the camera microcontroller. A basic GUI was created using TK inter module, which allows a user to save a parking location, remove a parking location, and exit the GUI using the previous LCD screen. Initial attempts to use the AutoCam to scan the QR code failed due to several out-of-memory errors and inefficient code that led to very bad FPS. The C-bar camera module, however, fixed all previous errors and allowed for a smooth and fast video stream. We use PyMongo module to send data to scan as a comma-separated value to the database. This data was first parsed to a JSON format using Python 3 JSON module. QR code generation. The QR codes are matrix barcodes capable of storing multiple types of data in many different ways. For our project, we decided to have the location of the parking spots of multiple garages and floors as a string that can be parsed as a JSON format, which is needed to input the database. For example, we use the garage I, floor 2, and spot number 3, as shown in the screen. This is the data that was parsed as a JSON and then sent to the database. The QR code allows for a certain level of error correction. We created the highest level possible of error correction for our QR code, which are proven to have up to 30% error correction capability. This is level H. For general purposes, lower levels of error correction will be sufficient. However, due to the nature of our placement of the project, we decided that wear and tear could be an issue, and we'll choose the higher level to help maintain the scalability of the code. QR code testing. During our demo, we tested the ability of the camera to scan the code from multiple distances and with different levels of light and wear and tear. While wear and tear were not an issue, light was a factor that affected the scannability due to the glare effect of the night vision mode. However, during our testing, the code was still scanned after backing up and parking the car again.
The next aspect of our design that we'll be discussing is the software development, in particular our communication and hosting services, which in our case is Heroku. For those of you who don't know, Heroku is a platform as a service cloud hosting that supports multiple different languages and add-ons such as Node.js, Java, and Gradle builds, which all of these are used in our design. Heroku is also free of charge, as well as not requiring the user to have prior knowledge or experience on managing environment or infrastructures. To set it up, you simply need to connect your Heroku app to GitHub, which ended up being super simple. Next is the database system we will be using, which is MongoDB. MongoDB is a non-relational database in which all components of our design will be interfacing with. The PCB and microcontroller will push information that needs to be sent to the mobile app to the database instead, making it a lot easier to control what goes in and out. Data will be sent and managed in the form of JSON that will be inserted into each collection. When connecting to the mobile app, you simply set up a connection string to your node.js code, making it very easy to connect to and debug. Our database in particular is set up by two collections, users and car locations. When the user creates an account or tries to log in, it will interface with the user's collection. On the other hand, everything in terms of the garage and car spots will be interfacing with the car locations collection. To save a user spot, the microcontroller will save the user's ID to the user ID field in car location, shown below. When developing our backend, we used a JavaScript-based runtime environment called Node.js. Node.js and Express dealt with all of our backend development with Heroku, as well as to MongoDB. To facilitate HTTP requests, we created get/post requests in our node.js files and hosted them on Heroku cloud service so that any of the applications can access it as long as they're connected to the server. In terms of the Android application connecting to the request, we use Retrofit, which is a HTTP client that converts your API into a Java interface, making it easier to use. For our mobile app, we designed it using Android Studios. In terms of mobile app development software, Android Studios seemed like the best option for us in terms of its features. Some of the features we took advantage of are its vast library and add-on systems, different GUI editors, as well as its longevity, making it a software that holds many tutorials and references. Looking at the sample photos below, you can see some of our UI design of the features in our mobile application. In order, you can see the first one, what the user sees when interfacing with logging in and signing up. Then, the activity in which the user finds where their car is parked, in which it displays a picture as well as the details oriented below. And finally, displaying the list of garages you can choose to see the capacity of. Next, we can see the mobile app use case diagram below. It starts off with the user navigating to the app in which they can sign in or up, which communicates to the database. After that, we reach the home page in which they can either go to settings, show available spots, or finding their car location. When going to the show available spots, you can choose which garage you would like to see and then it displays it. In terms of the mobile application development, a lot of the intended design ended up being pretty successful. The UI for the Android Studio development proved to be very simple and easy to use, as well as the additional libraries they offered. For testing purposes, the emulator integrated in Android Studios helped a lot with the debugging process as well. In terms of the app's runtime performance, it consistently connected and interfaced with the database very quickly, returning the results in a timely manner. At first, there were a lot of hurdles in terms of the mobile app. Initially, we had very little experience with Android development or any mobile development, which meant a steep learning curve. On top of that, the Heroku application was very tough to set up in the beginning, with the deployment as well as the HTTP requests in the backend. Even after all these challenges, we were still able to meet most of our goals for the design, but sadly couldn't reach some stretch goals that were theorized early on.
What went wrong? Obviously, COVID-19. We are four of us computer engineering students. We're not very proficient on circuits and electronics, so we needed a lot of research and time for those. So battery sensors and resistors, LEDs, the PIR sensors. We struggled a little bit with those, and what went right? We were very organized. We structured around, if we had informative group meetings, we started early, had good pacing, and good communication. Thank you so much for your time. I hope you all stay safe. This is all.